Good afternoon, everyone, and welcome. Thank you for joining the New Zealand Society for Earthquake Engineering August webinar round. Today's session is on the connection for low damage seismic design and retrofit of the precast floor, presented by Professor Rajesh Dakal, a name that really need no introduction. Rajesh is a professor of structural earthquake engineering and head of civil and environment engineering at the University of Canterbury. He completed his bachelor degree in civil engineering in Nepal, a master in structural engineering in Thailand, and a PhD from the University of Tokyo 2000. He is internationally recognized for his leading research on reinforced concrete buildings and seismic performance of the non-structural element. Rajesh has supervised about 50 postgraduate students and published over 500 peer-reviewed papers. He was elected president of International Spons Association from 2021 to the 2021 to the 2025. And he's delivered dozens of keynote internationally, including the ISET annual lecture. He has received the 2007 Ivan Skinner Award and the NZSEE Auto Global Award 5 times. A fellow of NZSEE and Engineering New Zealand, and Rajesh also has been editor-in-chief of the NZSEE Bulletin since 2014. It is wonderful Rajesh is presenting his work today with us and sharing his knowledge with us. And I'm very happy actually today. We have almost more than actually 200 people, 240 people registered for the today webinar, and this is fantastic to see that. It is amazing. And a quick housekeeping note, I just wanted to mention that as we have lots of people attending, please submit your question in the QA. You can see it in the top of the team in the QA session, not in the chat, so we can at the end of that manage it better, your question and your comment. Rajesh, over to you. Thank you so much.
Thank you, Niku. Kia ora, everyone. Good afternoon. Thank you for making time to attend this presentation. Today, I'm going to share with you a concept of low damage building system that we have been working on. And in particular, actually, a part of that concept is to avoid floor damage, actually, that the kind of damage that we have been seeing in recent earthquakes, especially those related to precast floor, right? So let me start by reminding everyone that we design our structures for life safety based on capacity design, relying on ductility and carefully detailing chosen areas of structural systems to dissipate energy through inelastic mechanism. In doing so, even in design level earthquake, we expect significant damage in carefully chosen areas. And in strong earthquakes, stronger than design earthquakes, obviously there will be quite significant damage to these structural components, making it dubious about whether they can be repaired back and restored to its pre-earthquake level or not. So here are just some illustration of some of the common structural system. And damage in concrete structures in particular, as you all know, is not easy to repair. You know, like there are mainly because of two things. One is by nature, concrete gets cracked, but inside the reinforced concrete, once they develop the plasticity, the elongation, the permanent extension of those plastic hinges make it difficult for these hinges to be repaired and look back like the original members that they were before the earthquakes. So, in particular, when these damages do happen to floors, that makes it even more tricky and more challenging to repair back. And in most cases, barring some exceptions, once the floors get damaged, the buildings end up being demolished and rebuilt. Right. We have seen several of those examples in recent earthquakes, right? Be it Canterbury earthquakes or even the Kaikoura earthquakes, where buildings in Wellington and Christchurch in these different earthquakes underwent significant damage to floor systems, and then that was one of the main reasons why these buildings had to be demolished. Precast construction is one of the common forms of construction, especially when it comes to concrete buildings. Do precast construction techniques help in like getting rid of this problem? Let's revisit that. The concept of precast construction is to assemble prefabricated components, but traditionally using on-site concreting for connecting the prefabricated components, and the end product is a monolithic connection. The advantages, claimed advantages, are quicker construction because you are not casting a lot of the structures and members on site. Better quality control because there are prefabricated components which are made in a quality restrictive or quality controlled environment in the factory, in the yard, and obviously less on-site labor and framework, right? However, the conventional approaches of assembling precast buildings by pouring concrete on site to connect between different components, that actually is counterintuitive in terms of those claimed advantages, because that requires framework and curing time for those on-site concrete joints, and which delays the construction process, or which does not give the advantage in terms of rapid construction as much as you like. And also, there are several issues with these monolithic precast structures or even traditional reinforced concrete construction. The first is actually these structures require demolition whenever you have significant damage after an event, or even without a damage, actually, if the property owner decides to change their plan and modify the structure or modify the functionality, or there are some changes required on the structure. More often than not, that has to be done through demolishing the building and then building a new one. And demolition by nature is a very disruptive process environmentally, which causes a significant wastage of materials which are non-biodegradable. That just adds to the landfill. It is a time-taking process. It costs a large amount of money and energy. I've given here in this slide, some numbers that validate these claims. Like one Christchurch building cost $10 million to knock down, and demolishing a typical 6-story buildings of 20-meter by 20-meter floor area, if you combine 75 of those, that is comparable to the atomic bomb that was, thrown, that was blasted in Nagasaki in after the Second World War, right? The other issues with monolithic precast construction, the one that we are directly dealing in this presentation, in this research, is vulnerability of precast floors, right? So precast floors, they are connected through a topping slab, with the structural members as our traditional practice. And such connections, they invariably damage in minor to moderate earthquake. You don't need a large earthquake for them to start creating cracks and incompatibility induced damage around the perimeter. And if the seating is limited, like for the precast floors, seating on the end beams, then because of elongation, they can fall which can lead to life safety hazards. Repairing floor damage is often very uneconomical and impractical, actually. Technically feasible, we don't know. There's a big question mark over that. But most of these buildings have been forced to be demolished after moderate to major earthquakes. And we are working on a low damage prefabricated building system that addresses these issues and several other issues that are inherent with monolithic precast construction. The first one, the issue is construction speed that I talked earlier, that the traditional precast construction limits this advantage, but this system that we are proposing is faster because it uses dry steel connections to connect structural members, all structural members between floor and frame, floor and wall, beam to column, column to foundation, etc. And it completely avoids on-site concreting. Second issue that I mentioned about sustainability, this system is greener because it completely avoids the need to demolish. It uses easily detachable connections to enable faster and easier deconstruction. And you can detach and demount components, and these components can be reused and recycled as we get another opportunity where the same type of connection or members are needed. The third is actually vulnerability of precast floor that I talked about. So this system that we are proposing is safer because it avoids the topping slab to connect with perimeter structural components, which means that actually the floor is connected to the structure through discrete floor frame connection made by steel members. So we don't have that vulnerability that is typical with the monolithically constructed precast concrete structures. The other issue is actually lack of seismic resilience, like in order to build back the building after some damage, because in concrete buildings, we have seen majority of the damaged concrete buildings being demolished and rebuilt. So this system will make the buildings more resilient because it uses low damage connections to join structural members between floors, beams, columns, etc. So in moderate level or even large level earthquakes, the damage will be heavily minimized. But when you have got very large earthquakes, the damage will have to occur somewhere, and we limit damage to easily detachable and replaceable components so that rather than thinking about repair, we replace those damaged components, and then in a short amount of time, we get a building which which is similar to what it was before the earthquake. So there is no ambiguity about can you repair it back to the level where before the earthquake, because in this case, like, you are replacing the damaged components, so everything is like new. So precast floors are vulnerable mainly because of the way they are connected. So this is the hypothesis, this is the preamble that I'm making is, like, even if you use a very stiff steel plate as your flooring system, but if you connect using the way that we are doing, because the floor system, the floor will get damaged. So it is not about the precast flooring member. It is about how we connect them to our surrounding structure. So that is the main reason that we are getting damaged. So, like the way that we use those topping slab with lightly reinforced mesh and the reinforcing bars going all the way to the end beams, that creates a moment resisting connection there between the floor and the beam, which is weak and fragile, right? So the moment resisting connection, but the capacity to withstand the rotation and moment is very limited. So because of that, actually, what we have seen is, the monolithically connected floors invariably damaged during structural deformation in minor to moderate earthquakes, and that is mainly because of displacement incompatibilities with the supporting structure. And all of you have seen these kind of illustrations showing the negative moment failure and positive moment failure in several other presentations about, like precast floor and hollow core floor in particular. So, like when the end beam has, or the building has to deform in one direction, there will be moments, negative moment being developed in that connection, which will create damage, like starting from the top. And when in the other direction, the positive moment that develops, then that will create crack from bottom of those floor slabs. And not only that, like when the buildings deform, the beams are trying to deform in that typical elastic double curvature, even in the elastic range, whereas the floor, they don't want to follow the suit of that, or follow that same pattern of deformation. So in that interface between the floor slab and the beam, there will be a lot of like conflicting stresses developed, which will create quite substantial damage during that interface. And not only that, when cyclic loading does take place, then as we know, the end of the beams where plastic hinges develop, these hinges grow in length, right? So which we call beam elongation. So in that case, actually, the columns are trying to move apart because the beam is getting longer and pushing the column outside, and that will create again another type of stress in the floor, which is connected to the beams. So that will exacerbate the damage even further, right? So we have seen this kind of like illustration based on concept, as well as that is the Clarendon Tower in Christchurch, where exactly the type of damage around the column in the floor beam interface was visible after the Canterbury earthquakes. So the design challenge associated with monolithic slab frame connection, like in addition to the issues that I talked earlier, there is further another issue related to strength hierarchy and seismic performance, which can be compromised. And in capacity design, like how important strength hierarchy is. Beam being weaker than the column is important because we want to control the performance of the structure by the well-detailed plastic hinges in the beams. So beams getting stronger, like in isolation, okay, anything getting stronger, you can imagine, think that, oh, this is good, like this, we are getting better performance out of the beam. But in a system level performance, beam getting stronger than the columns will be a disaster, because that will lead to an undesired column failure mode, right? So that is a typical, problem that we get because of these monolithically connected floors. Because when you have got floors connected to beam monolithically, then a part of the floor will participate in the beam strength, especially the like negative strength of the beam. But how much of the slab contributes to the beam? That's a question which has a lot of uncertainty. If you look at New Zealand standard, if you look Japan standard, US standard, they have given equivalent width of the slab in a different way, and they lead to different outcomes. Not all of them can be right. Only one of them, even if only one of them is right, the other are wrong. So that creates quite a bit of like risk in terms of the beam strength. Not only that, when the beams elongate, and like it tries to push the column up outside, the column tries to resist it, the axial compression is developed in the beam. And when the axial compression is developed, because there is an axial compression, the strength of the beam increases, because you can do the section analysis. If you have got compression force in the section, the moment capacity is higher, right? So these two things tend to increase the beam strength, which can alter the strength hierarchy, and even the failure mode of the building, which is undesirable. So in order to solve these issues, we have proposed a low damage floor connection. So in this research, we are focusing on this aspect, which feeds to the bigger aim of getting a low damage prefabricated building system as a whole. But here we are concentrating only on the floor to frame connections. And in this connection, the floors are connected to the surrounding frame by using steel angles which have got slots in the two direction as shown there in this figure, right? So and you can see like these angles will have a rubber bearing strip below the floor, and then the slotted hole where bolt is installed in a duct in the slab, and another vertical slot again another slotted hole where bolt can be cast in the precast beam. And in both sides, like because in the end beam you can see some stiffeners in the connection there. Let me see if I can show you. No, I cannot activate the pointers. That's fine, but you can see the end beams, the end connections. They have stiffeners because we want those connections to act as a backup in case unseating happens, like backup for the gravity system, right? So that the floor doesn't fall down. It is a redundancy, extra redundancy in supporting the floor. So this is the concept that we want to. Yeah, so the proposed floor frame connection, the floor looks like this in the surrounding structure. There are connections all around the perimeter. The key feature about this is that we don't put any connection, these discrete steel connection at the beam end where plastic hinges do form, and then because of the elongation, these connections can be disrupted, or these connections can like pull the floor together when the beam elongates, right? So these connections are all outside the plastic hinge region. That is number one. The second thing is this is how these connections are put at the two ends in section AA and section BB. And when the beams rotate in the two direction, there is no positive, like beam positive moment failure and negative moment failure, because the connections, especially with the slots in the two direction, can easily accommodate the relative movement between the floor edge of the floor and the beam. Similarly, you look at in the other direction, the same thing does happen, right? So it has got the ability to withstand that relative displacement demand between the floor and the supporting beam. So the slotted holes, they accommodate the relative displacement demand and help prevent damage to the floors. And this, instead of this kind of like positive moment failure in the traditional floors, now we have the floor deforming, floor and beam deforming the way that it is shown below in the illustration. Similarly, in the negative, instead of having that actually negative moment failure, the beam just moves outside, and the rubber pad underneath actually does allow some level of some level of deformation to accommodate that rotation, right? And the slot as well. And also, if you look at the side connection, because of the way of the side of the floor connected to the beam, there is no need for them to behave monolithically. So any little bit of additional deformation can be accommodated. So the connections are there to transfer the inertial forces, unlike in traditional flooring system where the inertia is transferred throughout the perimeter through the monolithic connection. In this case, the inertial forces are transferred through those discrete connections. And if you recall, actually, these connections, they have got, uh, the movement in the direction where inertia needs to be transferred is not restricted. So we have got slots in the other two direction where they can have relative displacement, but in the direction, that direction shown with the red arrow there in the bottom figure, there is no room for the floor to move, because any movement, any stress developed there is transferred directly through that connection to the beam, right? So that's how the inertial force is transferred. So this kind of connection has two possible applications. The first application is in new demountable buildings where the precast floor slab will be put on top of the beams, and then you can connect from the bottom using these connections as shown here in the new prefabricated building system. The second is actually it can also have application to retrofitting the existing vulnerable buildings with precast flooring systems, right? So how do we do that? Is actually, like you put these connections underneath and then fix them with the floor and the beam with post-anchored drills, with epoxy injected drills or any other post-anchored anchoring mechanism. And then you can cut the connection, the monolithic connection between the beam and the floor, and fill that with any compressible material, right? So with that, this is how it looks, and then you get exactly what we would normally do in new buildings, right? So experimental validation of the concept, let's look at it. This is the illustration of the test setup. We did this test in ILI lab in Tongji University in Shanghai, China, early this year. So there was a series of testing done. The specimen is as shown there in the right figure. The beams, the precast beams and columns, especially for the beams, they were cast with an end plate which had holes to bolt them and connect them to the column, and columns were prepared with the pre like pre-installed holes to take those bolts through, and the bars, reinforcing bars, were welded to those end plates, and then end plates had stiffeners as shown there. And then when they were fabricated and then connected at the site, this is how they look like. So the end plates were connected to the column face by bolting them through the holes which were already provided on the precast columns. And then after all the assembly, like the four beams and then the four columns, this is how the specimen looked. But there are some challenging bits here, because this is what we wanted. We wanted to test it in unidirectional as well as bidirectional cyclic loading. And when you do that, beams will elongate, and in order to not restrict the elongation of the beam, the bottom floor, like bottom support of the columns, had to be carefully designed. So what we had there is actually, out of the four columns, one column in one corner was pinned, and the two diagonally opposite columns were provided with linear bearings, whereas the one at the other extreme corner had bidirectional bearing, because the column had to move in both directions because the elongation could happen to both beams, right? So we pushed it, then basically the bottom slider would move outside, like I am showing here, the bidirectional slider as well as unidirectional slider at the top, at the bottom of different columns. But when we move, because of the beam elongation, the bottom slider would slide outside, and what it would result in is really two columns not being parallel. But we also wanted to maintain the parallel attribute between the two columns. So what we did is actually, that blue line that you see there is actually a steel beam which is connected to an actuator, right? Or like that actuator, the hand control system, we managed it to, after every cycle of loading, we adjusted that actuator, and then we made sure that the columns were parallel after each cycle, or at each peak. And then we followed up with the next cycle, did the same thing. Like, okay, it lost the parallel feature, and then the rotations of the two columns were not equal, especially in the large inelastic range of displacement. So that's how we managed it, right? So this is the specimen fabrication. We connected the columns and beams just through those demountable dry connections, and then we brought the precast floor, which was double T floor, and then we cast the topping on top of that. Please remember that actually, although the original idea is for new design, we wanted to prove that this can also be used for retrofitting. That's why we first connected as we do now. We get the vulnerable precast flooring system because of this monolithically connected topping, and then we prove that it can be used for retrofitting, right? So ultimately, after all the pouring, this is what it looked like, exactly like what we get in actual practice. And then we tested with conventional topping, so the testing was just pushing. You can see the actuators, one actuator from one direction and two actuators from the other direction. So when we started to load it, after first few small cycles, we already started seeing the damage, right? 0.28% drift. You can already see those damages in the floor to frame connections, and they are in line with what was observed in the recast test in Canterbury 2 years ago as well, and in literature as well, other tests, right? So what we did is actually no point carrying on, because we will get the floor damaged very badly if we proceeded. So we stopped the test there and we applied our retrofitting technique. So we just saw cut the connection between the floor and the beam, and then after that we put those dry steel connections with slots, as explained earlier, underneath the floor in different parts. And now you get a flooring system where, although there is topping, but the topping is not mechanically monolithically connected to the beam. There is a all around gap. Only around the corner, very close to the column, we could not cut because of the circular shape of the saw cutting machine, cut completely. So there was some small part which was still connected. Otherwise, it was all detached. And then we applied unidirectional tests up to 4.16% drift. We applied in one direction, gradually increasing displacement, and then we applied in another direction. And you can see the load displacement curves in both directions, very stable ductile behavior, as we see in, the monolithically connected frames, right? But you can see during these drifts that we applied, we started seeing the damage in the beams, and because beams were intentionally designed to be weaker than the columns, so they were controlled in design, and to damage was restricted in the beams as we had envisaged in the design phase. And 2.5%, which is typically the ultimate limit state, we started seeing quite significant cracks and yielding and plastic hinge formation. We continued the loading up to beyond 4%, where you could see clearly the bar fracture and quite substantial collapse of the beam, or the failure of the beam, we would say, right? But despite taking it to that measure, that much of displacement and causing so much damage to the beam, none of the damage passed onto the floor. You can see the damage stopped in the beam because there was no connection, mechanical connection between the floor and the beam, and the connection underneath gave up, or accommodated that displacement and deformation because of the slots. So in terms of beam elongation, we measured the elongation in the two ends of the beams and roughly got about 20-25 millimeter, like elongation at that final drift level. So altogether, the columns were moving apart by about 50 millimeter or so. Right, and even in terms of the vertical compatibility, like when the beams was trying to deform and vertically the floor didn't have to follow it because the slot in the connection underneath could accommodate that. So there was no problem, no damage whatsoever to the beam, right? So now post-earthquake repairability, because what we wanted to do was actually now these beam was damaged and as designed, and now we wanted to replace this with a new beam so that the structure gets completely new. Right, so damaged beam removed, new beam brought in, and connected again, through those bolt holes, and then bolts were tightened, and we get the structure as it was after that, actually, because you could connect the floor to the beam using the same angle connections underneath, right? So I can I'm showing you, actually, this is the first time the technicians in China were doing anything like this. We just explained the concept and they moved the beam out, the damaged beam out. They brought a new beam in, they fixed it, and all of that took 1 hour. And for the very first time ever. Right. So obviously, once they get used to nuances, the challenges associated with this phase, they can do it faster. But it was done. And then after that, what we did is actually now you've got a new structure now. Like all those damaged four beams were replaced. And now we have got four new beams. Columns were not damaged at all. Floor was not damaged at all. We have got all those slotted connections at the bottom and the beam to column connections as it was before. There was no sign of any damage. And then we could test again. And this time we tested bidirectional, like we applied the movement in both directions, right? So not just one direction. And we went up to 4.16% drift. And what we found was, again, as expected, there was absolutely no damage to the column, no damage whatsoever to the slab. All the damage in the large displacement regime was restricted to the beams, and the plastic hinges did form, elongations did occur, and the hysteresis loops that we got out of these tests were similar to what we got in the previous round. So changing the beam did have no effect whatsoever. So these are the bidirectional test results in the two directions, east-west and north-south. So as I said, physical response was similar to the previous test. No damage whatsoever to the floor and column. So these were the things that we already did in Tongji Aili lab in Shanghai, Tongji University. But as we speak, actually, we are doing a subsidiary test in University of Canterbury lab, because you can appreciate that those previous tests validated the ability of this system to accommodate the displacement demand incompatibility, right? However, their ability to transfer inertial force, like how much force each connection will transfer, because we need to design this system, these connections, right? So in order to know that, we need to test their capacity in terms of the inertial transfer. So these tests are being currently prepared. We have already cast the specimens and preparing the setup now. So the plan is to have, like two walls, concrete walls with one concrete slab and connected with these slotted connections. And then we push the slab cyclically to see how much these connections take, what are their failure modes if they have to fail, do they become the weakest link in the load transfer path, or they are able to successfully transfer the force to the beam in order to ensure that beam remain as the weakest element, how many and what size and what detail of these connections we need. All these questions need to be answered. So we are doing this. That is another phase. And also together, we are also doing numerical analysis, detailed numerical modeling to come up with, like the the detailed failure pattern of these connections, and then coming up with simple design equations so that designers can use. So to conclude, repairing seismic damage to monolithic concrete buildings is complex and challenging. Low damage demountable buildings solve this problem by enabling replacing damaged elements. Damage to precast floor is caused mainly by displacement incompatibility between the floor and frames or walls, depending on the structural system. The proposed connection circumvents this problem by providing slots that allow relative movement, but at the same time, transfer inertial forces, because in one direction, there is no room for it to move. It has to transfer the force. Full-scale tests have shown that the connection allows adequate ductile behavior of the demountable structure while permitting the floors to remain undamaged. And then the developed floor frame connections can be applied in new buildings as well as to retrofit existing vulnerable buildings with precast flooring system. Right. So with this, I thank the whole team, my PhD student Gonzalo, and my collaborator, Dr. Ke Jiang, Professor Santiago Puyol, and then the team at Tongji University, the master's student Dahua, and Professor Yiqiu Lu, who was my collaborator from Tongji University. So I thank you for your attention, and this is just a QR code to take part in a survey related to this demountable building system. There are just 4 or 5 questions, multiple choice questions. We would love to have your feedback, what you think, because you don't need to type any long message. You can just choose the answers from the options. That will help us plan our research ahead. So with that, I thank you for your attention and pass it back to Niku.
Thank you so much, Rajesh, for the excellent presentation. It's very amazing. You explained very well the different types of the failure. All of them is amazing. Just make it clear in the one presentation. So we have a QA. I couldn't see any question in the QA session. If you have any question, please add it there. In the meantime, actually, I have one question. So it is very amazing that with that connection, actually, the beam is not any damage happened for that. And this we are.
Yeah, Niku, I can see the questions there because I can see questions from Jeff Matthews here, Nick. Yeah, Nick, QR code doesn't seem to work. Okay. No, sorry for that. Actually, I thought this QR code works, but if not, then I will probably share a fresh QR code. But we would love to get some feedback from you, please. Yeah.
Okay, now I got it. I got it. It's coming up. So maybe we'll go for the next one. It is Jeff Matthew. Thank you for presentation. How economic is it to replace the demountable beam? How do you access internal beam? Do you do this? The fit out and facade will need to be removed. This may lead to the repair being uneconomic.
Okay, great. Look, I think, and who better to come this question from other than Jeff, right? Jeff, good to be communicating with you after a long time. So, here we have to keep in mind that actually the need to replace will be only in large earthquakes, very large earthquakes. When in a building, there will be many other components damaged and requiring attention, like including the non-structural elements, the building fabric itself, right? So we are intending to have a structural system that can accommodate moderate to design level earthquake with no damage, because the connections between the beams and columns will be low damage connections, like ultimately. But here, because the focus was only on floor to beam connection, we didn't use low damage connection there. We just wanted them to behave like monolithic, so that even for retrofitting of existing buildings, we could show some relevance, because in existing buildings, we have monolithic connections, right? However, like when in those large level of earthquakes, when many other parts of the buildings are damaged, this solution gives you an option of reusing the building by hopefully not adding to the complexity of the repair process, because this will not be the bottleneck. Bottleneck will be many other things in there, right? So what we have to compare with is actually with the current scenario, where at that level of earthquake, what challenges we get. Like most often, we will not be able to reuse the building, and even before we demolish the building, there will be a lengthy debate between insurers and building owners whether this is repairable or not. It will take years before they come to conclusion, and the downtime, which kills the loss, which dominates the loss. It is not just the repair process and repair cost, Jeff. The overall resilience is dictated by the downtime, right? So this is a way to, like, reduce the downtime, because there will be no ambiguity about whether you can bring back the buildings not to its original level. The second thing is internal frame. And this building, we are envisaging that there will be no moment resisting frame internally. Moment resisting frame or walls, whatever our seismic resisting system, will be around the perimeter, and internal frames will be gravity system. And these gravity systems, unlike in the past, we will connect with a pin connection, which will be which will incur no damage whatsoever. Currently, we design as gravity system, but we build as moment resisting connection, and that will give us damaged internal connections, as well as we saw in the Westpac building after the 2010-11 earthquake, right? So engineers were saying, oh, those are gravity systems, but the public were saying, oh, that is a significant damage, so how can we reoccupy the building? So all those challenges, I only presented a small part here, but the demountable building system is a whole lot of a bigger concept presentation, which I will do at some stage. Yeah.
Awesome. Thank you. The next question is from Holmes Room. How do you get strap into the beam at the beam and close to the column face under the steel gusset plate?
Sorry.
From the Holmes Room, they said, how do you get a strap into the beam at the beam and close to the column face under the steel gusset plates?
How do you, where is the, sorry, who is this question from? Let me read it.
Is this the Holmes Room?
How do you
Or maybe how to ensure the compatibility of the overall proposed lateral load resistance system with a large displacement 4 to the 6th story drift with non-structural and secondary structural element in the building and building fabric, like the glazing, precast facade, loading wall. I think it would be challenging.
That's fine. I would be interested to answer the previous question as well, so please get that back. But let me answer this question first. So look, I think non-structural elements is obviously is a big challenge in terms of building resiliency, right? So this system, if you look at the structural system that we are proposing, sorry, there is a noise coming through. Okay. So if we look at the building system that we are proposing, this does not add complexity to the non-structural element. Like we are still, getting the deformation that we were getting with monolithic connection displacement capacity, but those displacement capacity or the displacement responses of the structural system will add to the demand of non-structural element, right? So if the building deforms 3%, 4%, but it is not to, I didn't want to give a feeling that actually at a design level earthquake, this kind of building will deform to that 4% which we tested. We were testing only the capacity, right? So the idea is not to design buildings to go to that level in design level earthquake. So the non-structural elements can be, designed and provided to accommodate the drift demand given by these these type of buildings. So we will get maybe 1%, 1.5%, even up to 2%. We have got solutions on non-structural elements. So for new buildings, there is no problem, right? Because the whole building resilience as a system, we cannot just concentrate on structure and forget the non-structural elements, right? So non-structural elements will also have to be designed and fabricated or connected to the structure such that they can accommodate the demand, right? So this only solves the structural resilience, because in terms of the structural collapse, life safety, it is actually the structural system performance, and this does avoid completely the need for the buildings to be demolished and rebuilt because of structural damage that we have seen in concrete buildings lately. So non-structural elements, yes, agree, but there is no new complexity added by this system. And whatever problem there exists in the traditional system, the same problems do exist, but for new system, we do have to implement resilient and low damage technologies for non-structural elements. And my team have been developing all these solutions for quite many years now. So we have got low damage non-structural elements. Can you get to the previous question,
Yeah,
Niku?
sure. The previous question is from the Holmes room.
Yeah.
How do you get a stirrup into the beam at the
Stirrup.
beam
You're talking
end
about
close?
stirrup, right?
Yes.
Stirrup.
At
Okay.
the,
Yeah.
into the beam at the beam end close to the column face under the steel gusset plates.
Yeah. So the gusset plate, actually, we have got, like, Pawan did his PhD thesis. We did test a lot of solutions and finally zoomed into this, which we call end plated connection at the end. So the end plate has got those stiffeners which come inside the beam, and then the bars, the stirrup at the end actually are drilled through those stiffeners. There are some holes which go through, but look, I think those are also not needed, because we can weld those steel plates and the stiffeners to the main reinforcing bar. So only very close to the end, few tens, like maybe around 100 millimeter, we don't have that stirrup provided. But because the system is so integrated there, is actually there is no scarcity of the steel sections taking care of that shear demand. So damage is invited there, but collapse is prevented, right? So it deforms it deforms like a plastic hinge.
So, thank you. The next question is from the Puya. How should this connection behavior be captured in diaphragm grillage modeling?
Good point. Good point. Yeah, I think we are developing or we're still doing the numerical work, and which will add to the design. But at the moment, we can clearly see, because the connections are discrete, the uncertainty around the load transfer path actually in monolithic floor frame subassembly, because we have to make some assumptions about how the stresses and forces flow. But in this case, there is no uncertainty. So it will definitely have to travel through those discrete connections. But can we ensure that those connections are able to transfer the forces that come on them? That is actually the focus of the next phase of research that we are doing here at Canterbury. So the grillage modeling, I think in terms of concept, actually, because these forces being flowing through, or the strut and tie, for example. So simply like the load path is through those discrete connections. And where do we put those connections? How many? That is yet to be fully clarified, right? So we'll get to there.
Yeah. Thank you. Some related to that question. There's another person say that will the grillage be dictated by the connection point or vice versa?
Yeah. Look, I don't know if I get the gist of that comment, but yeah, as I said, like, because obviously it depends on the connections and those those modeling will have to reflect that, like, because we will have to, whatever elements that we model to represent the load path from floor to the beam, we'll have to go through those connections. So I think maybe we might need a separate discussion, probably offline on that, for me to fully understand actually where the question is coming from or what exactly is being sought. Okay.
Sure, sure. Good, thank you. The next question is from Chris. I would be interesting to see the next stage of the work looking at the connection. Did I ask this question? No. It has usually been difficult to get workable solution based on the strengthening offered by casting anchor or post-in solid anchor based on NZSE equation. Has any thought, investigation been given to the connection design at this point?
Yeah. Hey, look, I think that's exactly the kind of question. Conceptually, we knew that it would work, but there will always be question about, oh, does that post-anchor thing work or not? That is exactly why we did this test, to show that it works, right? So main thing is the strengthening, like retrofitting. In this test, we didn't test the ability of those connections to withstand the gravity load when the unseating happened, because despite putting that large deformation, 4% deformation, the elongation was not enough to unseat the floor. So we didn't test that aspect, whether those end connections were able to hold the slab without any seating or not. But what we did prove beyond doubt is, actually, if you do this, then despite the building moving significantly in large displacement range, there will be no damage to the floor, right? So that shouldn't remain as a confusion now after this test, because we can definitely get that. However, the question still remains in terms of the inertial transfer, because we didn't check the ability of these connections to transfer the inertial force. That's what will come in the next phase. But otherwise, in terms of retrofit, yeah, cutting those connections, still hopefully there is enough seating left, because if in the very old system we didn't have enough seating, but lately after Jeff's test, we did increase the seating length requirement substantially. Those seating lengths should be enough, but now these connections, they will provide the backup in case the unseating did happen, but it will definitely avoid damage to the flooring system in moderate to large earthquakes. Yeah.
Awesome, thank you. The next question is from Xavier. Since the connection only transfers shear, not tension, and this is a static test, the loading doesn't reproduce the slab inertial mass distribution from a real earthquake. That distributed inertia would generate a diagonal strut and therefore tension tie across the diaphragm. But this connection can carry tension. How is that tie force resolved in the actual design?
Yeah, look, I think in a way, like, you are only looking at one connection, Javier, because in one connection, you're right, there is no ability to take the tension, but the floor is connected on the other end as well. If you look at the other end, then any tension on the floor is restricted by that slot there. So as a whole in the system, we are providing all necessary ingredients as a system. But if a single connection, obviously there is restriction only in one direction. But the other direction, the connections at the other end, there is the restrictions in the perpendicular direction, which will provide the overall system level integrity and force transfer in all necessary directions. The only thing that we do not do is actually vertically between the beam or the frame and the slab. We do not transfer any forces vertically, because we want to allow the slab to remain horizontal, while these structural frames could move slightly vertically locally by different amounts at different places. Right? So we otherwise we have the mechanism to transfer the forces, even the tension in the floor slab, not in one connection, but by the other connection somewhere else. Yeah.
Thank you. The next question is from the Mark. The floor unit steel angle has a vertical slot which you are using to accommodate rotation, but how are gravity loads supported when there is no bearing connection detail in one image you show?
Sorry, read that again, please.
Mark Brown.
Mark. Yeah, so the question is about the gravity connection, is it?
Yes.
Yeah.
The gravity load supports when there is no bearing connection detail.
Yeah, so you can see because I will okay, so this slide that I'm sharing, if you can see the bottom right, the connection at the end with the stiffeners, like so. Typically, what happens is actually when these connections are provided, the bolts are close to the top of the slot, right? So when if and when the unseating happens, the floor will dislodge from the supporting beam and will fall into the top flange of these connections, right? So because the slot is already exhausted, then the bolt, the angle cannot go any further down, right? So it will sit there. So we will have to calculate, the bolt's ability to withstand gravity load, vertical downward load, and how many bolts we need. So the current test that we are doing at Canterbury also has that one additional factor built into the research questions, right? So if these connections are also required to take gravity in extreme earthquakes, like the connections, what is the gravity load capacity of these connections, and despite building some factor of safety, how many of these are needed and what size. So they are able to support the slab from the top, because the vertical slot has a distinct has a limited length, and in the initial configuration, the bolt is already close to the top of the slot at that end, right? So hope that answers that questions. Yeah.
We have a lot of more questions, but the time is finished actually, and I need to wrap up. And I think if you can, Rajesh, again, share your QR code, yeah, amazing. So if you have any question, please use that QR code. And I just want to say that this webinar has been recorded and will be uploaded to the NZSEE YouTube channel, so anybody could attend can watch it there later. And I just wanted to also remind you that we have a Pacific conference in February in Christchurch, and we are waiting to see all of you. Thank you, Rajesh, again. It was amazing. We have all of us have lots of questions. It is very great, and it is very great presentation. And you show all of the damage and the solution in this session, and it's amazing. Thank you so much. And I wanted to thank you to all of the participation that who joined us.
Thank you. Thank you very much, Nico, and thank you to all the audiences. I know that the QR code hasn't worked. I will share it. I don't know how we do that. Unfortunately, we missed the opportunity, but I'll try. But look, if you have any question or want to discuss, you know where I am. You can send either an email or we can chat in different phases. So I will be delighted to share more information on this system and this connection with you. Okay, thank you very much.
Awesome, thank you so much. So maybe you can send the email to the Rajesh or to the NZSEE, and then we pass it to Rajesh about your question. Thank you so much for participation. Thank you, everyone. Bye. Have a good day. Thanks, Rajesh.